Can everyone hear me? Hi, everyone. I'm Kieran Coulter from Cinderboss Communications, and today I'll be talking to you about workbenching Neural Audio DSP. Let's see. Yeah, you can follow along with the code. It's been just released. The code is my GitHub account /neuralplayer, and this talk originally stems as the second talk in a series after a talk at ADC 2021, juice development for Linux and Raspberry Pi. Of course, I realized after that talk it became very hard to get a Raspberry Pi during the pandemic. So, I started to broaden things and say, let's look at juice on the periphery of embedded audio solutions, try to make a general case for embedded audio. And I took a step back from that because I realized that maybe people were going to wonder what are you trying to deploy from software over to hardware, and decided to start to break this talk into several series. And that made me a little bit of a mix-up depending on where you looked what the talk topic was, but the other topic will be coming at a future ADC with a lot more context. So then I'm going to preempt myself and say, hey, maybe this is going to happen again, and are looking at it, some new FOSS features. I can't say which software, but this is going to enable a stepping stone to bring your plugin not directly to hardware, but something very similar to hardware through some open source software I'll be adding some features to. And then you'll have the full context all the way down to an embedded solution. So let's talk about the neural landscape. I would say on the design side, you're probably going to start working with PyTorch, very high level, and you could probably test your models in the Newton ecosystem. And that's really great when you have to rapidly iterate and continuously retrain. And once you got something good, you might decide to go over the Onyx exchange and bring your model over to TensorFlow for deployment. And I'd say that's the general consensus and the opinion. It depends if you're working in research or in industry. You might choose one or the other, and it's great that Onyx runtime and the Onyx exchange exists to bridge the gap. Of course, once you're going into embedded, the rabbit hole doesn't end there, because there's TensorFlow, and then there's TensorFlow Lite, and then there's TensorFlow Lite for microcontrollers, which doesn't even have a logo. So this rabbit hole continues, as my coworker definitely understands, and you might have to implement your own layers, implement your own operators, but pretty soon you've got a highly performant model ready to deploy to microcontrollers. On the real-time side, so basically when you're done with training, you're starting to look at inferencing. How can I get good performance? One great solution is Jatin's RT Neural. And you start to worry about, well, what kind of backend am I going to use? It's going to be Eigen, Xtend, or C++ STL. Of course, you can't really tell what's going to be the best choice until you try everything and see what works in your particular scenario. Another option, like you said, you only implement the neural layers that you need for your own project, and pretty much you have the same thing is the case for TensorFlow Lite for microcontrollers, where it's not a complete implementation. So it's great to build a community and make sure that all the layers and operators are available. I had to pick some neural DSPs to workbench for the topic of this talk. No better idea than to stand on the shoulders of giants. So everyone might be familiar with Splitter Deezer, source separation, and more recently Spotify's basic pitch, just for audio to MIDI, and that's what I selected for the talk. The next thing I was going to look at, okay, has anybody used this in the Juice community and tried to already do the same thing? I did find this as a real-time reworking of the Splitter model, and this guy, James Fung, decided to see how fast he could get it using his various options depending on the platform for matrix multiply. He was using Accelerate on Apple, OpenBlast on Linux, and MKL on Windows. And he was using the Intel MKL Fourier transform on all three platforms. On the audio to MIDI side, I also found NeuralNote. It was an entry in the recent Neural Audio plugin competition organized by the audio programmer in Newton. And those guys were using RT Neural, a combination of RT Neural and the Onyx. So, this is the basic idea. We're looking at separating out the vocals from the rest of the music and then running the vocals through basic pitch. And then you need some sort of player to synchronize the playback of the audio and the MIDI. And I decided, why not send the MIDI to a Rolly Lumi, so it's nice you can see the keys, the multicolored keys being driven. And this makes it a lot easier once Juice comes into the picture, because we can wire everything together and see what we get. So what do we have to do for Deezer Splitter? This is a basic idea. If there's one thing I wanted to convey during this talk, is that you might have your first neural DSP that you're trying to evaluate, and you're looking for some kind of course you can hear the results, and you have that qualitative analysis of how good the separation works, but what kind of quantitative analysis can you do compared to the baseline, which in this case would be the original vocal stem. So this is what we tried to do with Splitter RT. We wanted to compare the wall clock time against stock Splitter. It's about 7x speed up. There's a plugin version of Splitter RT as well, and check the real-time render latency of that. And most importantly, ensure that the MIDI output a little bit down the line is equally accurate to the stock. You can say the biggest optimization here, if you're working in neural audio, is not like saving the stage of the ratio mask for the final spectrogram. So that saves a lot of compute. And of course, the quality is lower, but in this case, we don't really care about the audio quality. We just are interested in whether we can get good MIDI at the second stage. So if you want to hear the difference, here's the original audio. We're no strangers to love. You know the rules, and so do I. And then here we have the Splitter RT extracted vocals. We're no strangers to love. You know the rules, and so do I. So that output's a little bit dirtier than the what I call stock Splitter. You can hear some of the artifacts left over from the percussion in many cases. So how are we going to combine these together? On the neural node side, we also want to compare the wall clock speed to stock basic pitch, because we've also noticed a pretty decent speed up there. And otherwise, neural node is just a means of workbenching the first neural DSP stage. And you can also get a sense of why, from the talk earlier today, why it's hard to put this sort of thing into a plugin format, because you don't have a lot of DAW supporting audio to MIDI. The other thing that's really challenging is getting these DSPs down to real time because of the types of techniques they use. And I saw this when evaluating both DSPs, that lower frequencies are going to require really long audio chunks to get the amplitudes for the lowest frequency bins. But that could be maybe solved in hardware a little bit down the line. So now you can see how this evaluation model is coming together. We run the output from the first neural DSP into the second one. And then we've devised a method of achieving qualitative analysis and quantitative analysis as well. We can hear the output, but we can also tell is the pitch accuracy at least as good or hopefully better than the baseline. At Cinevoz, we've used the exact same technique in speech noise removal from speech. So we combine the speech signal with noise, run it through a noise filter. And you can use mean opinion scoring to tell whether the average human would find the noise-filtered audio more intelligible than before. But to get a good second opinion, you could also use, in this case, speech-to-text engine made by OpenAI called Whisper, and then determine whether the word accuracy is better than or equal to the baseline word accuracy. Okay, so how do we bring this all together? We built something called Neural Player. This is often the development workflow for a lot of us. You know, this is a cutaway from a 3D model like Development Planet, right? And you're trying to shoot to the moon, and you're fighting developer gravity, right? So you have your idea, right? You always go to the left first, right? You want to do something awesome, but it comes at a cost, right? Your latency starts to go up, and you have to battle it back with some tedious fix to get it back to low latency, and then go back the other way, and then pretty soon you've got something that might be considered production ready, although I guess a lot of people release it's still in the yellow. So maybe we can lower the bar a little bit. The idea I originally wanted to do for this would be real-time show control, but it's really hard to get the latency to that point. So maybe a little bit less of A context where you really need to have low latency would be a media player. Maybe if you could do you could do processing of someone's music library in the background, and then have the results ready. They're not going to need absolutely that you have the lowest latency. And you should remember that this has all happened again 20 years ago. We're seeing the same scenario now with 2D convolution that we did more than 20 years ago with 1D convolution, where this principle was well understood in the 80s, but it wasn't until 1999 they were able to ship it in real time with Sony's DRE unit. So this is basically 3 different GUI screenshots from Neural Player. We have the main view in the middle here, and we have a separate hardware and software debug console. And this is mainly for people following these slides offline, but a quick and dirty UML composition of the software if you'd like to play around with the code yourself. A few notes as we went and developed Neural Player. Managing everything with CMake was definitely the only sensible choice. I started by making forks of these other open source softwares that I found and modifying them to make sure they were feasible for this type of workbenching. And it was really great with CMake. You could use CPM to manage all these dependencies. One new thing that I changed was using Git subrepo to manage the child repos rather than Git submodules. It just made it a lot easier to be able to commit changes to the subrepos, I should say, back to the upstream, working with different repositories as a single project. And finally, we built the player as an application that brings this all together. So a couple of other interesting branches in the source code. The Workbench 2 branch will allow you to compare against stock splitter or stock basic pitch yourself and compare the wall clock times, which are much longer, maybe due to adding emojis into the console. But and more recently, we added a visualizer branch. I don't know if anybody remembers Winamp, but it was a much-loved media player back in the day. And Project M is an open source version of Milkdrop, and we decided, wouldn't it be cool if you could extract the stem from the media player that you're playing and drive the visuals just with that stem behind the scenes. So you don't hear it, but the visuals are visualizing just the bass line or just the vocals. So the results, I would say, are, roughly speaking, Splitter RT is about a 7x speed up over the baseline. Neural Node is also much faster in its implementation, about 4x in that case. And some observations I found, and that's why the jury's still out on the results. The MIDI transcription was absent, I'd say below the alto tenor range, and this could be an optimization in Splitter RT to avoid processing lower frequencies. The last thing I noticed that was interesting is there were some MIDI artifacts littering the upper frequency range, and this could be unique to vocals because it's a lot harder to convert vocals to MIDI than a synthesizer. So without further ado, here's a demo of Neural Player. You have a Rolly Lumi. Confirm it is connected in the settings pane. You can also enable a MIDI hardware output here. Press Load New to render a new playlist. You can press Halt to interrupt a render operation already in progress. You'll still get a partial playlist of all files rendered so far. Press Load Existing to open a previously rendered playlist. Once the render is done, select a playlist entry and press Play to begin synchronized audio MIDI playback.
We're no strangers to love. You know the rules.
right. I want to say thanks to a few people, absolutely James Fung and the guys from Neural Note for providing the open source code to do the workbenching. Joshua Hodge, Shatton, and the guys from Newtone for developing the neural audio DSP community. I see great things ahead for us. And of course, Camille Kisiel, my coworker at Cinevoz, for clearing the way down the rabbit hole in front of us. If you want to reach me, you can reach me on my LinkedIn. And we're always looking for new projects at Cinevoz, in this case for neural audio. So get in touch with us if you'd like to help us develop your neural audio solution. Thank you. Are there any questions?
Hello? Yeah, I have a question. That was really cool. Thank you. Question I have is, so is it always outputting the MIDI based on the vocal? Or do you also have some choice in what it's tracking and outputting? Like which source?
Well, we're going to add some new options pretty soon. I mean, that David Hasselhoff song was my theme song for developing the source code very quickly after the talk acceptance, So this is just the beginning, I think. Bass is going to be a problem due to the low frequency, but it's a trade-off. Basically, optimization of latency versus some of these things that are harder to deal with in the system. So I think this offline processing of your music library just does it overnight, and you have everything. I think even in DAWs, it would be great if rather than having to process in real time, you could click like a freeze button or something, and it could pre-render the MIDI and then be able to play it back synchronously.
Thank you.